What's up, pussy ass pussy nation? My name's Flynn Scott Wilson, and your name is Flynn Scott Wilson as well, because you're a pussy. And let's go right on into this. Today's the 11th of November, 2021. It's a Thursday. I'm Flynn. That's Jazz. Say hi, Jazz. Say hi, Jazz. What's good, Jazz? What's good? What do I don't really speak English to Jazz. I kind of just make noises like a caveman. I go, what's up? Up and what about?
There we go. You don't like it up here, eh? Oh my god. What's she doing? She's on my desk. Why's she trying to go on my desk? I'm surprised.
Here you go, doggy. Who's a good doggy, huh?
Who's a good Yeah. I let you outside soon, Jez.
Okay, let's do some study, you pussy. A bunch of the stuff that I tried selling on Train Me currently probably will not sell. It probably will not sell, quite a bit of it. So I'll probably relist it at the same price one time. And for the stuff that just gets like no views at all, just like change the price next time. I can't wait to go garage sailing this Saturday and Sunday. I said that, huh? I don't know, do a garage sale Facebook. Cause I really wanna get naughty, and I think you're such a hottie. Oh, we got one. Yes, let's go. Whoa, is it fielding though? Oh, what the fuck? Sid Palms North though, so no fielding. Oh. I guess I could drive down to fielding. What time? 9 AM. Okay. Yeah, probably could. And I really want to get naughty, cause I think you're such a hottie. Play some video games, cause I love video games. Anyways, let's do some work, huh? Let's get to work all day, work all night. I work, then I twerk. But some of the stuff that I bought is gonna sell though, immediately. Now we have 3 bids. Let me look at my current items. Call of Duty World at War Final Fronts, $8 bid. That's good. That didn't sell last time when I sold it. I started the listing at the exact same price. That's kind of cool. Black Ops 3 PS4 game. That was mine. Current bid $25. That's cool. Work all day. Champion Return to Arms PS2 game. I bought like 9 games for $7. And current bid is at $40, so instant dub, instantly made back all the money of all those games, of this one game. And it'll probably go for higher, because someone sent in an offer of $50, and we've got 5 bidders and watches. So let's go, that's cool. And then Wii Cricket Game, that was in the same bundle of those games, $15 current bid. That's pretty cool beans. Work all day, work all night. Then I twerk all day and twerk all night. Cause I work. Okay. I'll probably use a Learn Coach. Let's quickly write up a to-do today though. Why did I quit out of that, docs? Work all day, work all night. Yeah, I work. Okay, change motorcycle word at some point. Oh my god. Yeah, I'll do 4 cycles there. I'm gonna shut down the Shocklock website actually. Cause I work all day, work all night, and I twerk all day and twerk all night. So look at my billing. Hopefully billing. Where's my next bill, Joe? No. Oh, are you serious? Is today really the day? What the fuck is my password? Is it this? I think, dude, the billing thing might have been today. I think I might have gotten away with it, Mum. I think I just got away with it. Let's go. That's $50 saved. Let's get it. 11, 40, 12, 20. That's the file. Keel, we've got my to-do today. Keep on forgetting, like, I stopped talking for ages. I forget that. I'm doing a little podcast here. Not trying that hard, though. Lucky dog. Okay. Dude, I gotta... Okay, let's see where that dog is. She isn't on her mat. I think she actually really wants to go outside. Work all day, I work all night, and then I twerk all day and twerk all night. Because I work all day, I work all night. My the shirt I just remembered I was wearing for like way too long. You let spread. Is that how you let spread? What is it? I don't know how to let spread. Anyways, I work all day, work all night, and then I twerk. Twerk all day, twerk all night, and I work. Okay. Let's go. Oh, this glass as well. As I work all day, all night, and then I twerk. I twerk all day, I twerk all night. Let's study then, huh? Ugh. Can I come on in? No, I can't. Okay. Let's just create a new tab, drag it out. Close train me on that one. To do today, I always have open just down on the bottom of the screen. So what's the future like, huh? How is virtual reality coming along? Is that going good? Is that a big thing? What crazy scientific stuff has been discovered? Anything serious? Anything really cool? Anything about dark matter or dark energy or anything? No? I was really into that one stage. That sciencey stuff. Feel like I could be again. 11th of the 11th of November. So let's open my Feynman Technique doc. Let's open my 2014 doc. Let's open up Anki for my note taking. Let's drag this on over here and plug my laptop into charge. Let's go. That's what it makes. It goes. Chuck Anki down there. Put the little flash card thing over here. label this thermochemistry. Keel. I work all day, I work all night, and then I twerk. I twerk all day, I twerk all night, and go berserk. Go stupid, go crazy. Kia ora, may the course be with you. Whoever designed this website did a good job. Wonder what it was designed through. I don't know. Chemistry. Nah, I want thermochemistry, I think. Yeah. Oh, there's a lot. Oh no. 1, 2, 3. Only 3 things. Okay. Let's go. Let's watch this video.
Hey there guys, and welcome back.
Me, fat face. My name is Pussy Fat Face. And this is my video. Okay, let's go.
To Chemistry 3.4. In this PowerPoint, we're going to be looking at graphs of state changes. And so this is essentially a graph that shows what happens as you heat a group of molecules up. So as you heat something, you would expect that it would get hotter and hotter. That is, as you increase the amount of time you're heating it for, the temperature will also increase. And you'd expect that to happen in a linear sort of manner. However, this is not the case. The actual graph looks like this. So you have linear sections of the graph here, here, and here. But you also have flat sections. And we're going to look at that and we're going to explain why that is. So what you've got to understand here is that these flat areas are where you're putting in energy and changing the state of the molecule. For an example, you start with something as a solid and you heat it up. You heat it all the way up to its melting point, where it's going to melt and turn into a liquid. At this time, the energy you're putting in isn't heating the solid anymore. What it's doing is it's breaking the bonds. And it's breaking the bonds using the delta heat of fusion that we talked about to turn the substance into a liquid. After that, the liquid is heated all the way up to the boiling point, and after that, the heat of vaporization is required to break more bonds. The key concept here is that the heat energy you put in isn't always going to heat up the molecule or group of molecules that you're looking at. Once you get to the melting or boiling point, all the energy is going into breaking the intermolecular bonds. Once the bonds are broken, the structure of the group of molecules changes, and it changes from solid to liquid or liquid to gas. The same thing happens in reverse. If you're going from gas to liquid, you cool down your gas, and then for a while, energy is released as bonds are made until it turns into a liquid. Always remember that the making of bonds is something that creates energy. It's exothermic. So here's a summary of what I was just going through. You have a solid, you heat up that solid until it's at its melting point. MP, as we have here, the dotted line.
This stuff,
from A to B is the process of breaking the bonds, aka melting, and so the amount of energy from A to B will be the delta heat of fusion. Once the entire reaction's taken place, all the solid has turned into a liquid. This can also go the other way. As I said, you can go from B back to A, and that process is called freezing. And once again, the amount of energy that's required to turn a solid into a liquid is equal and opposite to the amount of energy required to turn a liquid into a solid. So then we have a liquid, and that liquid is heated up, and that happens in a linear fashion until it reaches boiling point. At boiling point, the energy is used to break intermolecular bonds in the liquid, letting it become a gas. And this is also known as the heat of vaporization. And that's what we see C to D here. The other way around, we call it condensation, and again, it's equal and opposite to the heat of vaporization. Finally, we have a gas, and we can heat that gas up as much as we want. For our purposes at this level of chemistry, nothing else happens aside from a hotter gas. So that's what I'm showing here. A gas, and we can heat that gas up as much as we want. For our purposes at this level of chemistry.
What the fuck was that about? What the fuck was that about, Jimmy? For our purposes, at this level of chemistry, what the fuck else can happen? Hey? You're from a gas to a fucking plasma? Is that what you're saying? What the fuck else can happen, you little fuck?
nothing else happens aside from a hotter gas.
Yeah.
So that's what I'm showing here. The linear increase, so the temperature increases from whatever it starts at to melting point, and then it increases from melting point to boiling point, and then from boiling point onwards. So as we learned a couple of PowerPoints ago, strong intermolecular forces mean higher melting points and higher boiling points. And so if something has a higher melting point, that means the intermolecular forces between it are strong, and it takes more energy to break the bonds.
What the fuck? Load, you pussy. Why isn't this shit loading? I've got internet. I knew it's always super sus when... Whoa, what's going on there? Do I only have 25 minutes? You gave me 30 minutes to study. What the fuck was that about? Hey, fuck you. Oh shit. I'll be back. Dude, they gave you a... Why the fuck does my room smell? Is it me? Is that why my room smells? Dude, they give you a 25-minute timer? Fuck you guys. You fucks. Get unlimited time, oh. $104 a year? Fuck you, buddy. Fuck you. What if I downloaded a video somewhere? Oh man, I thought it would be really good to... That's actually really smart of them. Whoever designed this website is fucking good, man. I don't think this is a Shopify website. They're nasty with it. Alright, let's just do the one that I'm really struggling with. I'll do enthalpy calculations. And intro. How long are the videos? I've only got 25 minutes left. Can I not even watch? Is it saying it's locked? What? Why would it be locked? All I want to do is learn. Dude, what the fuck? Is it because I haven't resumed the timer?
Hey there guys, and welcome back to Chemistry 3.4. In this PowerPoint, we're going to be looking at graphs of state change.
Yeah, it was.
Hey there guys, and welcome back to Chemistry 3.4. In this PowerPoint, we're going to be talking about enthalpy calculations. How is enthalpy change measured? How do we know for a reaction how much energy is given off? And the best way we measure this is we measure it experimentally using the experiment below. In this experiment, some of you may have done it in class, you have an insulated vessel and you put in a known amount of water and reactant. You then quickly add the second reactant, and that's a known amount of the second reactant as well, and you put the lid on. The lid has a hole for a thermometer. You measure the initial temperature before the reaction occurred, and you measure the temperature after the reaction has finished. And the temperature change is related to the amount of heat absorbed or given off. And that sort of makes sense. If the reaction is producing heat energy, that heat energy is going to go into the water and heat the water up. Equally, if the reaction is not producing heat energy, it requires heat energy, then the heat of the water is going to decrease. And we relate it using this equation here. Q, the amount of energy, equals M times C times delta T. M is the mass of water that you're heating up in grams. C is the specific heat capacity of water, and that's defined as the amount of energy needed to raise 1 gram of your substance by 1 degree Celsius. And for water, the value is 4.18 joules per gram per degree Celsius. And delta T is the change in temperature. So let's look at a quick example of that. So you've got a question that's asking you to calculate the energy gain when 250 mils of H2O rises in temperature from 25 degrees to 50 degrees Celsius. And so you've got a mass, a C, and a delta T to work out before you can answer this question. Luckily, for water, 1 litre of water is 1 kilogram, and 1 milliliter of water is 1 gram. So the mass is 250 grams, because the volume is 250 milliliters.
4.18.
Remember, for this equation, that grams
Q
need to be
equals
used,
250
not
times 4.18
kilograms.
times
The
25.
specific heat capacity of water does not change, and so
Skip forwards.
H you find is going to be equal to the delta RH standard. And most likely it is not. And the reason that's not is because no experiment can be run perfectly. And running your average everyday experiment in the lab is going to be run far from perfectly. So what are some of the things that could change your delta RH to make it further away from delta RH standard? Well, the first could be you're not doing it in standard conditions. For the calculation to give you the correct value, you need to be doing it at 298 Kelvin and at 1 atmosphere of pressure. If you're not doing it under these conditions, you're most likely going to get a value that is different from the delta RH standard.
Okay. 2 reasons for incorrect practical enthalpy calculations. Not under standard conditions. Trust me.
Hey there guys, and welcome back to Chemistry
Fuck.
RH, as you need to deal with this issue of to the surrounding. Often at this point in the question, they might ask you whether the delta RH you find is going to be equal to the delta RH standard. And most likely it is not. And the reason that's not is because no experiment can be run perfectly. And running your average everyday experiment in the lab is going to be run far from perfectly. So what are some of the things that could change your delta RH to make it further away from delta RH standard? Well, the first could be you're not doing it in standard conditions. For the calculation to give you the correct value, you need to be doing it at 298 Kelvin and at 1 atmosphere of pressure. If you're not doing it under these conditions, you're most likely going to get a value that is different from the delta RH standard value. In addition, delta RH standard is calculated in a laboratory with cutting-edge technology. If you're doing an experiment just in the lab, it's most likely that some of the heat energy is going to be lost into the surroundings, for example, lost through the beaker into the atmosphere. So if they ever ask you why your delta RH is going to be different from delta RH standard, those are generally pretty good reasons to go
I
to.
wasn't listening.
The lab, it's most likely that some of the heat energy is going to be lost into the surroundings, for example, lost through the beaker into the atmosphere. So if they ever ask you why your delta RH is going to be different from delta RH standard, those are generally pretty good reasons to go to. But back to the relationship between Q and delta RH. And the best way to think of it is Q is the amount of heat absorbed or given by the water, and delta RH is the amount of heat absorbed or given by the reaction. So the first thing to consider when trying to work out the relationship between Q and delta RH is you need to deal with this issue of delta RH being measured in kilojoules per mole, while Q is only measured in kilojoules. And to do this, you plug it into the following equation. Delta RH equals negative Q divided by N. So you need to divide it by the number of moles of reaction that's occurring. You may also wonder why it's a negative Q, but if you think about it, it makes a bit of sense. Q is the amount of energy absorbed or given off by the water, whereas delta RH is the amount of energy given off or absorbed by the reaction. And you can see those things are going to be opposite to each other, because if the reaction's producing heat, it itself is losing energy, while the water is gaining energy. Equally, if delta RH is endothermic, so it's taking energy from the water, the amount of energy in the water is going to go down, which means the delta RH will go up. So if the temperature of the water decreases, the reaction is endothermic and delta RH is positive. And if the temperature of the water increases, Q is positive, the reaction is exothermic, and delta RH is negative. So let's apply that to the same example we did before, except with an extra portion. So the first part of the example is exactly the same, and we've plugged through to find that the Q value is 0.679 kilojoules. Now we need to find the delta RH for this reaction. And they've given us the concentration of NaOH and HCl at 0.1 moles per litre. So we straight away go to this equation, and we know that we need the number of moles. And so to get our number of moles, we get our concentration times our volume. So 0.1 for the concentration times 0.025 for the volume in litres, and that gives us our number of moles. We now know the number of moles of our reaction, and we can work out the delta RH. A little trick they might throw into this question. They may give you a different concentration for NaOH and HCl. And what do you do then? Which one do you turn into number of moles, and which one do you use in your delta RH equation? You always use the smallest number of moles that you've found. And that's because the reaction can only happen until one of these things runs out. And so the smallest one is going to always run out first. And so the smallest number of moles is the number of moles of reaction that's going to occur, because it can only occur while both reactants are present. So that's a little trick they throw in there to try and catch you out. So what do you need to know for enthalpy calculations? You need to know that they are measured experimentally, and you need to have a rough idea of how that is. You need to know these two equations. Q, the energy absorbed or given off by the water, equals the mass of the water times the specific heat content of the water. Water equals the mass. Two equations. Q, the energy absorbed or given off by the water, equals the mass of the water times the specific heat content of the water, which will be 4.18 times the change in temperature. The only other thing they could really do to try and mix you up is they could give you a different liquid, and if they give you a different liquid, so it's very unlikely, they will have to provide you with a C value and just use the C value they provide you instead.
They have to.
The other equation you need to know is that delta RH is equal to negative Q over N, N being the number of moles. So let's smash through one more example before we finish up for today. So 25 mils of 1 mole HCl is added to 25 mils of 1 mole NH3 with a temperature rise of 6.5 being recorded. This is for a neutralization reaction which produces ammonium chloride in water. So what they want us to do is calculate the delta RH for this neutralization reaction. They're telling us that the mass of the mixture is 50 grams, Q over N. Is probably heat loss through the beaker and experiment. So that is a very count experiment. H for this neutralization reaction is negative 54.3 kilojoules per mole. They might follow that on with this question. When the delta RH was found experimentally in the school lab, the value obtained was lower than the theoretical value. Account for the differences in the values and suggest how the difference could be minimized. This is a very common theory question for this part of the course. And so what you say to that is easy. You say that most likely the conditions were not standard. You were not conducting the experiment under standard conditions. In addition, there's probably heat loss through the beaker and into the...
Cool. Entropy.
Hey guys, today we're going to go...
Hey guys. Pussy ass pussy here. Cool. Okay. Let's have a break. Let's have an early break. Got 5 minutes left on the clock, so I'll just come back and cancel the 5-minute timer. I'll see you guys in 5 minutes. Hold tight. I'll be back. Look at that pimple. I'll be back. Oh, I hit 90 kilograms on the bench. I don't know if I said that. And getting stronger on the bench. 70 for 5, easy. 75 for 4, ishy. But my 75 for 4 and 70 for 5, I'm doing with very good form. Where I come down, controlled, pause there, and then up. Whereas my 90 for 1, when I did 80 for 3, it's just no pause, coming up a bit faster as well, going down a bit faster. Anyways, I'll be back. I'm gonna get some brain food. I love brain food. Nature enter me. It's a beautiful day and I can't stop myself from smiling. Can't stop myself from denying. Can't stop myself from lying to you every day. Oh man. Okay. Let's check my emails. Beaumont. Yeah, that was fudge stickles, huh? Okay, so fudge stickles has paid. That's cool. That's very cool. Cheers for that, fudge stickles. Appreciate that. My main man. Let's go on. Learn, coach. Let's learn some coaching. Okay. Instantly quit that timer. Resume timer.
Hey guys, today we're going to go through the last topic, entropy. But before we get on to talking
Why is this quality so dog shit?
about entropy, we've got to define something called a spontaneous
Oh, there we go.
reaction. A spontaneous reaction is a reaction that proceeds without any outside force.
Whoa.
So once you've started the reaction, it will just keep going by itself. It doesn't need you to keep adding anything. A good example of it is like a fire. So you have to get the spark to light the fire, but once the fire is lit, it will keep burning spontaneously. It doesn't need you to keep putting energy in order for the fire to keep burning. Another example is water condensating on a glass spontaneously. It doesn't need you to keep putting energy in for that to occur. And spontaneous reactions are often exothermic. In fact, they're almost always exothermic, because if it's exothermic, it's not requiring energy from the surroundings to power it. And so just a reminder, delta RH is negative, bonds are made, and heat is given off. However, there are some spontaneous reactions that are not always exothermic. For example, ice melting occurs without you needing to keep putting in force. However, that doesn't seem to make sense, because you're breaking bonds as you melt ice into water. And if you're breaking bonds, that should require energy. And the reason that ice melts spontaneously is because of a second thermodynamic property we have to consider, and that is entropy. Entropy is just the measure of disorder in a system. So it's how organized or not organized a system is. For example, here we have a low entropy system because it's very well organized. Whereas here we have a high entropy system because it's not very well organized. So that's all it really means. But how does this relate to spontaneous reactions? Well, one way of reading the second law of thermodynamics is that in any spontaneous reaction, the entropy of the universe will increase. So in all spontaneous reactions, entropy is increasing and things are getting more disordered. You might think that doesn't really make sense, because sometimes, for example, when you turn water into ice, the water is getting more ordered because it's going from being floating around to being in a specific structure. And you're correct, but you've got to look at a wider view of things. While the water is turning into ice and getting more ordered, we know that that's an exothermic process, so it's releasing energy, and that energy is going into the environment and making the environment more disordered. So every reaction, entropy of the universe has to increase. Try not to get that confused with what I was saying before. The entropy of every single reaction doesn't have to increase, but the entropy of the entire universe will. So here's an example of what I was just talking about.
You've got a carbon footprint and also an entropy footprint.
Over time, this wood is not going to rearrange itself into a neat, organized stack, and that sort of makes sense, because you wouldn't expect it to. If you leave this wood long enough, it will form this messy stack eventually, because things will fall off, the supports might fall over or rust over time. You can see entropy everywhere in real life. Again, here's another example. If you were to have red jelly beans and white jelly beans, and you were to mix them up, you're increasing the entropy of the system, because everything's mixed up. If you were to get this, pour them out and resort them so that all the white's at the bottom and all the red at the top, then you're decreasing entropy. And it's in this direction that does not happen spontaneously. So luckily for entropy, there are actually no equations that they expect you to know. What they expect you to be able to do is talk about it and understand when a system is getting more disordered, so increasing entropy, or getting less disordered, so decreasing in entropy. So they might say, ice turning into water is a spontaneous process. However, it is also endothermic. Explain why the reaction occurs spontaneously. And you would say something like this. Ice melting is spontaneous. However, the delta fusion, H, is positive because you're breaking bonds, so it requires energy from the atmosphere. However, this positive delta H is offset by an increase in entropy because you're getting significantly more disordered. Because the H2O is going from a solid where it's locked into a particular structure to a liquid where it's free to move around. And so because entropy offsets the enthalpy, the reaction overall is spontaneous. So what are some of the factors affecting entropy? Well, first, there's the physical state of the substance. Things that are solids, as I've sort of talked about earlier, are locked into a rigid matrix and they can't move out of that matrix. So they're very ordered. So they've got low entropy. Liquids, they've still got some order. For example, if I put liquid in a cup, it's not going to just spontaneously jump out of the cup like a gas would. It's moderately ordered, and so it's got a moderate entropy. Gases, on the other hand, have high entropy because they're not ordered at all. It's very difficult to hold a gas in a particular shape. It just likes to float away. So the second factor affecting entropy is volume. So for gases, increasing volume increases the entropy. For example, children inside a classroom here, there's not much room for them to move because they need to sit at their desk, and so you've got low volume essentially. So if you want to increase entropy, you might put them out on the playground outside their school. So out on the playground, there's heaps more places they can be, and they're moving around much more randomly than they were when they were sitting in the classroom. So it's more disordered, and there's a higher entropy. The third thing is temperature. An increase in temperature equals an increase in entropy. And this is the reason why exothermic reactions generally occur spontaneously. Because in an exothermic reaction, you're producing heat to the environment, and when you put heat out in the environment, you're causing the environment to become more disordered, and the reaction is more likely to occur spontaneously. So as temperature increases, particles move faster, there's more random movement, and there's more disorder. Finally, it's the number of particles. The more particles in a system, the higher entropy. And that sort of makes sense as well. If you've got more people walking around or running around, if you look at it as a whole, each individual one is doing their own random little thing, and so there's more random ways of arranging the particles, more randomness in general, and thus more disorder and more entropy. And here is how we apply that to chemistry. If you have N2 plus 2H2 going to 2NH3, you've got 3 moles of stuff turning into 2 moles of stuff. So this would be a decrease in entropy. So for number of particles, you just want to look at how many particles are in gas form, and it's important that you only do gases for this. So N2, I haven't written it, but it's a gas, so you got 3 moles of gas turning into 2 moles of gas, which is a decrease in the entropy. If N2 was, something else that was a solid, you would not include it when you were counting the number of moles of particles, because you only count them if they're gas. So if we think about this again, entropy in terms of enthalpy, in exothermic reactions, heat is transferred to the surroundings, the temperature increases, particle movements increase, disorder increases, and entropy increases. This is why exothermic reactions are quite likely to be spontaneous. Endothermic reactions, on the other hand, are the opposite. They take heat from the surroundings. So the temperature of the surrounding decreases, the particle movement in the surroundings decreases, disorder decreases, and entropy decreases. And so for an endothermic reaction to occur spontaneously, so because of this, all this stuff here is decreasing entropy of the environment as a whole. In order to offset this, your reaction must be increasing entropy quite a lot. If the amount of entropy in the reaction increases by enough, the reaction will occur spontaneously. So let's look at a summary chart of what I've just talked about. Changing physical state from solid to liquid or liquid to gas increases the amount of particle movement, increases the random motion, increases the disorder, and increases the entropy. Increasing the volume means that there's more room for the particles to move, and so their movement increases. And because they've got more room to move in, their random motion increases, disorder, and entropy both.
I wonder if he's picking up parcels or not.
Let's fight. Alright!
All my parcels have been picked up, being delivered to my Trade Me customers. Resume timer.
Hey guys, today we're going to go through the last more room for the particles to move, and so their movement increases. And because they've got more room to move in, their random motion increases, disorder, and entropy.
Yeah, we get it, bro. Shut up.
Increasing the disorder of the environment and favouring the spontaneous and water. To increase entropy quite a lot to make up for the entropy it's stealing from the surroundings. So let's look at an example question. Hydrazine is often used as rocket fuel. When liquid hydrazine undergoes...
Hey, this is from an exam. I remember this.
Combustion, it forms nitrogen and water. In the reaction here. Explain why liquid hydrazine readily burns in oxygen. You should talk about enthalpy and entropy.
Okay, so what do I think I'd say here? Hydrazine is... Why is he going so slow? Is he turning around? Is he saying, "Listen, what have you done? You fucked up?" Ooh. Undergoes combustion and forms nitrogen and water. Right. So because... let's just see what it says.
Answer first is enthalpy. Enthalpy is negative, so it's an exothermic reaction, which we've written here. Exothermic reactions form products that have a lower energy than their reactants. That's one way of saying it. Or you could say the energy is released when this reaction occurs into the environment, increasing the disorder of the environment and favouring the spontaneous/forward reaction. And then you need to...
Enthalpy change. The combustion is an exothermic process since it's negative. Exothermic reactions form products that have lower energy than reaction/energy. And this favours the spontaneous/forward reaction. What the fuck?
Talk about entropy.
The combustion reaction has more gas molecules in the products. This goes from liquid to gas, thus increasing the number of particles. Therefore, the entropy of the system increases and this favours the spontaneous forward reaction. Both entropy and entropy are favoured, then hydrazine readily burns this reaction.
Which one of those four factors we talked about is occurring here? Well, we've got 1 mole of gas turning into 3 moles of gas, so that's a good start. There's an increase in the number of gas particles. Let's see if there's any of the other ones. The temperature, well, there's not huge evidence the temperature of the reaction is increasing. And if we go back here, there's also no increase in volume, and there's some state change occurring. So we want to talk about the two things. So the combustion reaction has more gas molecules in the products than in the reactants. This means some of the reactants are turning from liquid to gas form, and gases here are more disordered and have a higher entropy. Because of this, the entropy of the system favours the spontaneous reaction. And then a final tying off sentence, as both enthalpy and entropy are favoured, then hydrazine readily burns and the reaction is spontaneous.
Dope.
Alright, let's just do one last example question. Ammonium nitrate dissociates in an endothermic reaction as shown in the equation below. NH4NO3 is a solid, going to NH3 plus HNO3. Below is the table outlining the 4 statements about changes in entropy that may occur during any endothermic reaction. tick to the left of any statement that is correct. And here are our 4 statements. The entropy of the system increases, the entropy of the surroundings increases, the entropy of the system decreases, and the entropy of the surroundings decreases. So let's think about this. It's an endothermic reaction, and so it's stealing energy from the environment to power the reaction. And so that's going to decrease the temperature of the surroundings, which means that the molecules in the surroundings are not going to be moving as fast, so there's going to be less disorder, and there's going to be a lower entropy. So the entropy of the surroundings, everything outside of the reaction, is decreasing because you're stealing energy from it to power your reaction. The next question is, where is that energy going? And the energy has to be going into the system. So let's have a look. We've got something in a solid form being turned into 2 gases. So we have 0 moles of gas here and 2 moles of
endothermic reaction. That means that energy is required, is taken from the surroundings into the system, which means that which increases the speed, and that means that the entropy of the surroundings decreases as the particles move faster, and the entropy of the system increases.
Of gas here. And so what we've talked about with those 4 points before, solid, liquid, gas. The solid with low disorder and low entropy has been broken down into 2 moles of gas, which has high entropy. And so if we've gone from low entropy to high entropy, the entropy of the system meaning the reaction, has increased. So here's our justification. As the solid is converted into a gas, the random motion of the particles increases, and so entropy increases. So that's why I've ticked our top one. And for the bottom one, as it is an endothermic reaction, heat is taken out of the surroundings, decreasing the temperature and slowing particle movement. This results in a decrease in entropy. And so this is how you'd answer another type of question they might ask. So that's all from me, guys. Good luck for your external. I'm sure you're going to do fine. So thanks for taking the time to listen to me, and good luck. I'll see you later.
Fuck you. I'm sure you're gonna do fine. Okay, buddy. Okay then, buddy. Let's see what happens when the time runs out. Let's watch enthalpy. Did I listen to...
Hey there, guys, and welcome back to Chemistry 3.4. Acquire energy. H2O is a liquid. When they give you... It's quite an easy topic to start with. You just need to know this is the heat of carbon dioxide. They apply to everything. Anything will have a standard enthalpy of fusion. Anything will have a standard enthalpy of vaporization, etc. So any substance could have this, and you just need to know what it means when they give you this number.
Oh, that's
the
easy.
Final one, and probably the most common one we're going to deal with, is delta FH standard. And this is the heat of formation. So it's saying, if I was to form something from its individual elements, how much energy would it give off, or would it take? So if we're looking at NaCl, we're forming it out of Na, and we're forming it out of Cl. Here are our reactants here, and you're forming it from the elements in their normal state under standard conditions. So what I mean by that is that to work out what state your reactants are in, for instance, I know chlorine's a gas because chlorine is a gas at 298 degrees Kelvin. Na is a solid at 298 degrees Kelvin, and NaCl is also a solid. So you just use whatever form they're in at 298 degrees Kelvin. And this situation tells us that delta FH, so forming NaCl from its parts, gives off 411 kilojoules per mole of energy. So a quick summary of enthalpy.
What I just said, the energy of the water. Oh, the timer ended. What happens? Time's up. Finish this activity. Okay, finish current activity. Okay.
It's quite.
Oh, they let me. Oh, that's nice, then. Oh, dope. I can just watch this entire video.
Being made.
And that's cool. You can travel the world, but nothing comes close to the night ghost. Go from here. Okay. Q equals the energy of the water. So the energy released, or... Because energy... So the heat energy of the water will increase if the reaction is exothermic, it gives off heat, and it will decrease if the reaction is endothermic, takes in heat. Think of Q over N is equal to the standard enthalpy change. That's pretty cool. That's just the energy released or gained from the system, from the reaction. Spontaneous reaction. A spontaneous reaction occurs when the change in S minus the change in RH, the change in enthalpy is positive. Exothermic. Exothermic reaction is a reaction that gives off energy, puts energy into the surroundings. Factors affecting entropy. That's a great question. So we've got the volume. If it's gas, volume. We have the number of moles. We have the temperature. And we have another thing that I can't remember. Okay, there's my thermodynamics done. Let's listen to this video.
286
And then
kilojoules.
I'll just watch like YouTube videos. I want to do some practice questions as well, man. Usually they have practice questions.
We can tell that by the negative side per mole of reactant. So let's talk a wee bit about state changes and how they relate to enthalpy. The easiest one to do this with is water. Water has three forms, we know. As a solid, we call it ice. As a liquid, we call it water. And as gas, we call it water vapor. Or some people call it steam. State changes refer to the changes from one of these forms to another one of these forms. So from solid to liquid, liquid to gas, or vice versa. And when this is happening, bonds are being broken and bonds are being made. So in a solid, there's a lot of bonds. If you're going to turn into a liquid, you need to break some of those bonds, and breaking bonds requires energy, making it an endothermic reaction. If you do the opposite, if you've got water and you're turning it into ice, it actually produces energy because you're creating bonds, and creating bonds gives off energy once the bond has been made. So we have special names for these. And the first one we're going to look at is the delta FUS of H standard. So H just means the heat energy, standard, as we know, means under standard conditions, and delta means change. The FUS stands for fusion, and fusion being melting. So when they talk about the delta FUS H standard, they're talking about how much energy is needed or is released to turn 1 mole of H2O as ice, as a solid, into 1 mole of H2O as a liquid. And we know that's plus 6 kilojoules per mole. The positive meaning the reaction is endothermic and it requires energy. So another one we can look at is delta VAP for H standard. And that stands for the change in heat energy when you're vaporizing something. And so that means you're turning something from a liquid into a gas. So to turn something from a liquid to a gas, you need to break bonds. And when you're breaking bonds, you require energy. H2O as a liquid, turning into H2O as a gas, has a positive delta VAP.